talk a little bit about my project, Mathematical Justifications for Musical Scales. So kind of a central question we can frame all of this around is, why do some scale sizes appear more commonly across different musical cultures? For example, many musical practices have scales with 5 pitches and then pentatonic scales, or 7 pitches and then you can think of the white notes on the piano, or 12 pitches and then you can think of all of the notes on the piano. And this picture shows 2 Javanese gamelan tunings, which respectively have 7 and 5 pitches. The vertical bars indicate the pitches and where they fall in relation to the Western chromatic scale, which is a 12-tone scale. So 5, 7, and 12 again. So yeah, how might we justify these choices mathematically? That's a good starting point for this. So to do this, first we have to set up our mathematical framing of scales, and then we have to provide criteria for optimality of scales, and we'll have a couple of different criteria. Once we do that, we'll go over some equivalent, like logically equivalent characterizations of these criteria, which the first one comes from continued fractions, which we'll talk about. The second one is called well-formedness, which amounts to a kind of symmetry in the scale. And the third one is called Myhill's property, which has to do with the distances between the pitches in the scale. And as Professor Mark said, we'll use a common framework of irrational rotation maps on the circle, which we will also talk about. So if we want to define what a scale is, while the conception of a scale and the exact structures it includes varies from culture to culture, what's pretty common is that there's this notion of a set of fixed pitches, each with an associated frequency, which you can think of as the fundamental frequency of that pitch. And for our setup, there are 2 desirable features. The first one is octave equivalence. So if I sing these 2 pitches, la, la, the fundamental frequencies of those are in a ratio of 2 to 1 to each other, and we would want those to be considered equivalent. That's pretty universal. And that would also require that the highest frequency in the scale is no more than 2 times the lowest frequency, which is what that inequality shows. So that's the first thing. The second one is that we want to have a nice way to represent what we call singularly generated scales, which are scales you make by choosing an initial frequency, for example, 200 hertz, and then you keep on multiplying by the same frequency ratio, such as 3/2. And it turns out that a good system to build in both of these is, instead of working with frequencies directly, you take them log base 2 and modulo 1. So pitches become numbers that are in the interval 0 to 1, not including 1, and they're equal to the log of the corresponding frequency over the lowest frequency in the scale. And to kind of illustrate this, first we get octave equivalence from that. The lowest frequency, nu naught, will become log base 2 of nu naught over nu naught, which is 0. And then if we take 2 times that, the log base 2 of that over nu naught is 1. So we can visualize the interval 0, 1 as the unit circle, where 0 is the rightmost point, and we go counterclockwise until we get back to the origin, which is also 1. And then, so in this system, 0 and 1 are considered equivalent because frequencies who are in a ratio of 2 to each other are considered equivalent. So that's the first feature. And for the second feature, if we have our singular generating interval or frequency ratio, this becomes what's called a rotation map. For example, if we tune using the frequency ratio of 3/2, which is called a perfect fifth in Western music, or Pythagorean tuning, this becomes, instead of multiplying by 3/2 over and over, with a logarithmic scale, we are successively adding log base 2 of 3/2, which we will call alpha the generating interval. And we will use this for all of the examples in the presentation, but all of our results will apply to any irrational value of alpha. And then just the third reason is like a logarithmic system, instead of working with the frequencies directly, kind of agrees with how we hear the distance between pitches. If I sing twinkle, twinkle, little star, and I sing twinkle, twinkle, little star, the difference between the frequencies of each adjacent word or pitch is different between the first time I sang that and the second time. But the log of the ratios the ratios of the pitches are the same. So the log of the ratios are the same. And this is a nice way to think of that in terms of addition instead of multiplication. Cool. So with this, we kind of can start building our definition of a scale. So a scale is just a finite subset of the interval from 0 to 1, not including 1. On the left, we see that we can label the pitches in a scale, which are just numbers, in ascending order with S subscripts. So the highest pitch in the scale is Sn minus 1, and we call this an n-tone scale because it goes from S0 to S sub n minus 1. On the right, we have the singularly generated scale, where you can see alpha is drawn as that arc. And here we start at the pitch at 0, which we will call the origin, and we iteratively rotate by alpha to get what we call the iterates of the tuning process or the scale, and we label those with R subscripts. So we start with R0, and then we rotate by alpha to get to R1, and then you keep rotating by alpha to get to R2, and so on until you get to R6. So we have that iterate order, the order that we tune the scale in. But we can still label the pitches in terms of the scale, the ascending scale order, which you can see in green there. And then, yeah, a couple more things just to hammer it in. I have this little video that shows why it's called a rotation map if you didn't already pick it up. If you ignore the theta, ignore the light blue thing, and ignore the binary sequence on top, what this Wikipedia graphic is showing is just that you're rotating by the same angle. The blue dot is rotating by the same angle to get each new iterate of the rotation map. Yeah. Note that the S's, the scale order, is dependent on where you stop, what the value of n is, what the last iterate you generate is. For example, if I had stopped at R5 instead of R6, then that R6 wouldn't have been there, and then R4 would have been S2 still, but R1 would have been S3 instead. I have a couple of videos to just hammer this in one more time because it's super important for the rest of the presentation. So the first one shows this tuning process, but we're just starting with an initial frequency and we're multiplying by the same ratio without doing the mod 1, without putting it in scale order. So you'll hear that here. So that's how you would tune the scale if you just keep going up by that 3/2 ratio. Now we can do that, but we take all of these mod 1, we put them in the same octave so that none of the frequencies are more than 2 times the initial frequency. And then finally we do that, but we play it in the order of the scale, which is in clockwise order. Okay, so hopefully that's clear by now. we're going to go on and look at our criteria for optimality with this system. Actually, we're not. This is the formal definition. It's just what we said. The RJ we call the jth iterate. That's the only new thing here. So 0 is 0th iterate. And yeah, it's just the multiples of the multiples of alpha mod 1, going from j equals 0 to j equals n minus 1. And that's all. So if we want to think about when these singularly generated scales are optimal, one way we can think about it is this. So we start at 0, we generate all of our pitches, and if at some point we hit a pitch that is pretty close to the origin, pretty close to 0, we can just round off that pitch to the origin and consider the scale of all the previous iterates to be optimal. So there are two senses that we can think of this. First is when the iterate Rn is neighboring, which this means it's closest to the origin compared to all of the previous iterates that are also above or also below the origin. So in this case, R7 is neighboring because it's closer to the origin among all iterates above the origin. And then here also R5 is neighboring below the origin because it's closer than all iterates, previous iterates below the origin. So in this case, we say that, that iterate is neighboring, and in this case, the 7-tone scale and the 5-tone scale generated by alpha are both optimal scales of the first kind. Now there's a stronger notion where instead of just being the closest either above or below the origin, the iterate is actually the closest out of all previous iterates. And in this case, R5 is the only closest iterate because it's closer than R7. Well, that doesn't actually matter. Because it's closer than all iterates R0 to R4. However, R7 is not closest because R5 is closer than it to the origin. So in this case, we call the 5-tone scale generated by alpha to be an optimal scale of the second kind. And that includes R0 through R4, because again, we are saying R5 is close enough to the origin that we just round it off. So, and you might have picked up that optimal scales of the first kind of the second kind are automatically optimal scales of the first kind. R5 is the closest out of all previous iterates, so it must necessarily be the closest out of all previous iterates that are below the origin. And musically, I kind of alluded to this, but the intuition is that by rounding off the closest or neighboring iterate, you are forcing the scale to be closed, where the pitches in the tuning process are all alpha apart from each other, but the final one is something close to alpha away from the origin. So in that sense, you're kind of forcing the scale to be closed. And here, again, the suggestion is to truncate your tuning process once you have 5 pitches or 7 pitches. Okay, so with that, now we're going to talk about some equivalent ways of thinking about these scales, which I think is kind of cool because they're not intuitively, like logically equivalent, but you can prove that they are. So the first way comes from continued fractions. And before we get to it, here's just very quick background. If alpha is irrational, it can be uniquely expressed as an infinite continued fraction that looks like this. It's just an infinite nested fraction with these AIs. And then you have to prove that, but we'll just accept it for now. And then we can define the convergent fractions of alpha to be that, but you truncate it at a sub n. And we call that, so you can evaluate it and it will be a fraction, we call that p sub n over q sub n. And if you accept the top expression, then it seems plausible that the limit of the p sub n over q sub n would be alpha as n goes to infinity. So that's that. The thing we're going to take from this is the denominator is qn. And it turns out that the indices of the closest iterates, which are the optimal scales of the second kind, are just the convergent denominators, Q sub n, of the continued fraction expansion of alpha, which is cool. And then the indices of the neighboring iterates, which are the sizes of optimal scales of the first kind, is given by the set of intermediate denominators, which are calculated from the convergent denominators, according to this expression here. I'm not going to go too much into the intuition about intermediate denominators, etc. But what we can get from this is that continued fractions provide an explicit algorithm to find sizes of optimal scales of both kinds, which is cool. And if we do this for alpha as log base 2 of 3/2, which is that perfect fifth we were talking about earlier, the intermediate denominators are 1, 2, 3, 5, 7, 12, 17, and so on. So we kind of have this, like, you might speculate, like this sweet spot where there's enough pitches in the scale, but there's not too many, and they're also optimal. And that's 5, 7, and 12 pitches. And then I just bolded the convergent denominators, which are 1, 2, 5, and 12, but not 7, interestingly. So, yeah, so that's cool. What I did in my project was I gave a proof of one direction of the second item in that theorem. The first item is pretty quick to show. The second one, Professor Marx gave a proof of the direction where if J is an intermediate denominator, it must also be a neighboring iterate, index of a neighboring iterate. So I actually used that fact to prove the other direction. And it was based on kind of the geometry around the circle with rotation maps, as opposed to like doing this long algebraic proof using continued fractions. So that was fun. All right, so the second equivalent way we can think about optimal scales is called well-formedness. And here we're framing it in terms of the relationship between the two orderings of the scale. The iterate order, which is the order we tune the pitches in, and the ascending scale order, which is the order you hear it in if you sing up the scale. And if you notice in this picture, we have the scale generated by our same nice generator, the perfect fifth generator, and it's a 7-tone scale, so that means an optimal scale of the first kind. And if you notice, the first scale order pitch is R0. Sorry, the 0th scale order pitch is R0. The S1 is R2, S2 is R4, S3 is R6, so it's going up by 2 each time. S4 is R1. You have to think mod 7 because there are 7 pitches in the scale, and so on. So here, you can always get the iterate index of any pitch by multiplying the scale order index by 2 and then taking it mod 7. And that turns out to be true in general for all optimal scales of the first kind, which are, again, the ones you get from the neighboring iterates and rounding those off to the origin. You can obtain the iterate indices in scale order by multiplying the scale order indices by the same coefficient, which in this case is 2, and we call it the ordering coefficient. And intuitively, this kind of means that within each scale step, that represents the same number of iterations in the tuning process. So in that sense, there's kind of like a local symmetry of the scale, where the first 2 pitches are 2 tuning steps apart. The next 2 pitches are also 2 tuning steps apart, and so on. So here's the formal statement for that. If we consider the permutation of iterate indices in ascending scale order, so here, the I subscripts are just the iterate indices as you go counterclockwise around the scale. We say that the scale is singularly generated, well-formed, if that permutation is an automorphism of the cyclic group of order n. We call it the ordering automorphism. If you've taken group theory, cool. If you haven't taken group theory, that just boils down to, for our purposes, what we just talked about, that there's this coefficient q that we can multiply the scale order indices by to get the iterate order indices. And what's cool is you can actually determine what this q is. It's that. one thing to notice here is that, or one thing I'll tell you here is that q sub n minus 1 and q sub n k minus 1 represent the two indices of the iterates that are neighboring to the origin. One is above and one is below. So one of them is going to be the first scale pitch above the origin. And if you let j equal 1, you can see that this means the first scale pitch will be q. So that kind of agrees with itself there. What I did for this, I kind of clarified and restructured the proof of if you have an intermediate denominator, it's also the size of a singularly generated well-formed scale. And then I gave an alternative proof of the other direction, which again was more based on the circle and rotation maps instead of so much algebra, and it was shorter, which was cool. Yeah. So the third thing, the third equivalent characterization of optimality we're going to talk about is called Myhill's property, and we'll build up to it a little bit. So if you notice here on the left, we have, sorry, the colors maybe aren't so favorable for this, but you can see where the pitches are. On the left, we have the 7-tone scale generated by the same value of alpha, and you notice that between adjacent pitches, we call those gaps. There's only 2 different sizes, which are color-coded as green, red. Whereas on the right, we add in the 7th iterate to make an 8-tone scale, which is not optimal. And here there are 3. Now we can go up to 12, which is an optimal scale of the second kind even. And here we notice there are 2 gap sizes. And then on the right, we add in our 12 to get a 13-tone non-optimal scale. And we have 3 gap sizes again. So what you may have guessed from this is that a scale is an optimal scale of the first kind, or a rotation of it, which just means you rotate everything. That's not super important for this presentation. If and only if the scale has 2 distinct gap sizes. And one thing that I think is important, or one interpretation I have of this at least, is that the scale has no holes in it, and I'll show you what I mean. If we look at this example of the 8-tone scale, one can show that if you have the 3 gap sizes, the smaller 2 gap sizes add up to the bigger gap size. So here, green plus red equals blue. Now here, like if this were just a blue interval, there would be no 7 here, but there is. So there are some spots in the scale where this size of interval is cut in half, not exactly in half, but in half by another pitch. But the other spots where this interval occurs, it is not cut in half by another pitch. Where if we were to just generate a few more pitches, all of those would be filled. So that's what I mean when I say there's no holes in the scale. Yeah, and then now we can generalize this into what's called Myhill's property. So instead of just looking at, adjacent pitches, we look at pitches of an arbitrary number of pitches away from each other, which we can formalize by defining intervals of the scale to be ordered pairs of 2 pitches in the scale. We call the span of the interval the difference between their indices in scale order. So gaps are intervals of span 1 because in the scale order their indices differ by 1. And then we call the size of an interval just the counterclockwise distance between them on the circle. And Myhill's property then is a generalization of the 2 gaps thing we just talked about. Oh, I forgot to mention one thing. The 2 gap thing is equivalent to what's called the Steinhaus conjecture, which is a famous here. Yeah, shout out to Steinhaus. But Myhill's property states that not only do the gaps come in 2 sizes, but if you consider any arbitrary span d, the intervals of S with span d come in 2 sizes. So yeah, and for this, I also kind of elaborated, clarified the proof, and put it in terms of irrational rotation maps. And the musical intuition, or one quick musical intuition for this, is that if you think of just the white notes on the piano, there's the interval of a third, which is a span 2 interval in our system, and there's like a major and minor intervals. There's major and minor thirds, which give rise to major and minor chords. So yeah, so that's one connection. Here we can see with the 7-tone scale there are only 2, if we consider intervals of span 2, which are pitches with 1 pitch in between them, there are only 2 sizes of those intervals. There's the green plus green and the green plus red. There's no red plus red. So there's my proof. Yeah, and then other than this, I proved more specific information about the gaps and intervals of scales, what the exact sizes of them were, what the exact sizes of gaps and intervals are, what the counts of them are, like how many small gaps, how many large gaps are there for a given optimal scale. How do you decompose, say, a span 4 interval into gaps, because it's just made up of 3 gaps. 3? Yeah, I think 3. How do you decompose it? How many large and small gaps is it made of? And then a thing we've been doing more recently is looking at a measure called the balance of a scale, which is, if you consider all the points around the circle, it amounts to the center of balance of all those points, which is somewhere near the middle of the circle, or the magnitude of the center of balance. And we showed a certain upper bound on the balance of optimal scales for the first time. And hopefully we can show more bound, like a lower bound on that. But yeah, that's all I have for you. If you have any questions about either of these, I have some extra slides if you're curious about it. But that's all I have for you. Here's an AI-generated image that I plugged in a bunch of keywords from my project.